Hello students, this is Jagan Babu, Assistant Professor, RMD Engineering College, Kavarapete, Department of EC. The subject from first semester to last semester plays a very vital role, that is called DSP subject, Digital Signal Processing. Yes, we are going to see the subject, DSP subject. This is for third year students, 6th semester. We are going to see unit number 2, IIR filters, Infinite Impulse Response Filter. We call this IIR filters. We have two types of filters, IIR filters and FIR filters. One is called as finite impulse response, other one is called as infinite impulse response. Infinite impulse response filters are finite impulse response filters are there they would obey linear phase. Here it does not support linear phase. It contains of both poles and zeros. In FIR it contains only the zeros, no poles over there. That's why there is no denominator in the any kind of equation. Here you will have the equation both numerator as well as the denominator. Okay, we'll see the topic. The topic is nothing but IIR filters. Point number 1. We have the analog filter in the IIR filter is Butterworth filter and Chebyshev filters. Number 1, Butterworth filter. Properties of Butterworth filter. The properties of Butterworth filter are whatever given today class are very important repeated university questions, 2 marks. Mostly they asking properties. Properties of Butterworth filters. The properties of Butterworth filters are number 1. The filter order capital N completely specifies the filters and as the value of capital N increases, the magnitude response approaches the ideal response. We have two response. One is called as ideal curve, other one is called the transfer curve or normal curve. The order filter, you are going to find the order filter N. Once calculated the N value using the formula of the Butterworth filter, once got the N value, it completely specifies the filter design and you have to find the N increases. Based on the N increases, based on the N value you will get the magnitude response. From the magnitude response, you have already will calculated the ideal response. For any kind of filter such as low pass, high pass or band pass, you need to compare both the filters. Number 2. At the cutoff frequency omega c, the magnitude of the normalized Butterworth filter is 1 by root 2. Any curve if you draw, you have to take the bandwidth as 1 by root 2, that is called 3 dB. 0.707. There you can calculate the bandwidth of the high frequency as well as the low frequency of the any low pass, high pass, band pass and band stop filters. Butterworth filters are all pole design. That's what I said. Here you have the poles, the Butterworth. It will be based on only the poles. Denominator, there you are going to design over there. This is the question, properties of Butterworth filter. Short you need to understand. Point number 1, it's going to say about the magnitude response approaches the ideal response. Point number 2, you know very well, 1 by root 2 times. Point number 3, you know very well, it's a pole design. Next, properties of impulse invariance. The properties of impulse invariance techniques are number 1. Poles in analog filter map directly to poles in the digital filter. That is a transformation pk equal to e power sk into t. Poles in the analog filter map directly in the digital filter. We have analog filter and digital filter. Impulse invariance is a digital filter. Butterworth is an analog filter. We can map directly both analog filter using digital filter. The formula is p suffix k equal to e to the power of s suffix k into t. Number 2. It preserves impulse response and shape of the frequency response if there is no aliasing. Aliasing should not take over. That's what we will be studying the sampling theorem. There we are studying the Nyquist rate, right? There should not be no aliasing. Once there is no aliasing, impulse response property obeys. That is impulse response and shape of the frequency response. It preserves. It's going to preserve the impulse response and shape of the frequency response. So therefore, it's calculating the h of n as well as the h of j omega for any frequency term. See to that there should not be no aliasing. Desired transition bandwidth map directly between digital and analog frequency domain. This is a one important keyword, that's a transition bandwidth. We'll be calculating the bandwidth, that is a 1 by root 2 times from the analog filter to the digital filter transformation. Here we need to calculate. That's going to be a desired one. So instead of you are saying it's a normal frequency, called as a desired frequency response or desired frequency. This is mapped directly both the signals of analog and digital. For any impulse invariance technique, the S-plane intervals ranges 2k minus 1 by t into pi or 2k minus 1 pi by t. This is a pole design. This is a pi value. Pole design calculating for the impulse invariance one is 2k plus 1 divided by t for k equal to 0 to 1, 2k minus 1 by t for the any intervals, ranges from positive value to the negative value to the positive values. It going to lies map directly to the Z plane, UV. Hope you understood the two important University 2 mark properties of impulse invariance and properties of Butterworth filter. Thank you. More videos we'll see in the next